doing is intersection of two planes. And if two planes cross, they either intersect at a line. If they do not intersect, they must be parallel, or they're the exact same plane. Those are the three conditions when you're looking at intersection of a plane. Okay, so we want to look at how you solve intersections of planes, like given two planes, right? Pi 1 and pi 2, how do you find where they intersect? Now, this is going to be a detour from what we've been doing yesterday. There's something different that's required. All right, so we want to solve this here. So if everyone could look at this equations here, notice what we have. It's very different than what we were looking at when we were looking at three equations, three unknowns. I now have two equations, three unknowns. So if you look at these two planes here, here's the observation. Sorry, guys. The plane here is 1 minus 1, 1. And the plane here, N2, is 1 minus 1, 1. So the observation here is we have two planes like this, where the normals are actually exactly the same normal, right? You can see that. Like if you grab the normal off this plane, you can see it's the same normal here. They share the same normal, right? It could be in a different location, but it's the same normal. So because of that, because the planes share the exact same normal, these planes must be parallel. And therefore, in this situation here, we have no solution to the question for this example, right? The idea here is that these planes are parallel, like they share the same normal. Now, it could be the case that they're parallel, but the exact same plane. But if you notice here, like 4, 0, 0 is a point on plane 1, but 4, 0, 0 is not a point on plane 2. So now I've shown that they're parallel and distinct. Let's use that terminology, parallel and distinct. See that? So that's like one of the cases, right? Now, how did I come to that conclusion and not go into the parameter argument that I went into? Is you have to first look at your plane, and then you say, okay, what are the normals of the plane? Are they parallel? Are they the same? In this case here, these two planes share the exact same normal. So since the planes share the exact same normal, so that's like an observation you'll have to do initially. Since the planes share the exact same normal, you're either in this situation here, or it's the exact same plane, right? So you're either in case 2 or 3. If the normals are equal to one another or scalar multiples of one another as well, you could come to the conclusion that it's either case 2 or 3. What I did next is I just randomly picked a point. So this point here, 4, 0, 0, I just made a quick observation. I looked on this plane here, and I saw that 4, 0, 0 is on this plane. And then I made the observation it's not on plane 2. So therefore, the planes are distinct. So therefore, we have parallel and distinct planes, and you have no solution. So we go to our next example here, same idea. Take a look at the normal. Okay, so normal 1 is 1, 2, minus 3, and normal 2 is 4, 8, minus 12. Okay, so what's the conclusion here? Well, that means that the normal, like N2, is actually equal to 4 times the normal 1. So therefore, either these planes are parallel and distinct, or it's the same plane. It's one or the other here. Those are our options. Is everyone kind of with me so far? Right? But if you take a look here, you just take equation 2 and divide by 4, you've actually created the exact same plane. So this is the exact same plane. So the conclusion is same plane, infinite solution. With this one, it's different. You take a look at the normal, you look at normal 1, we got 1, minus 1, and 1. I take a look at the normal for this plane, we've got here 2, 2, and minus 2. Now, it may look like it, but these are not scalar multiples of one another, right? Like N2 is, if you want, it looks like they could be, but it's off by a minus sign. Can you guys see that? So N2 is not equal to K times N1 for any K value you choose. Like any real number you take, there's no way to make these equate. Or, yeah, right? Are we good with that? Okay. So, okay. So the conclusion is now, therefore, back to what we initially talked about, like our first diagram here, where case 2 and 3 are not possible. Therefore, it has to be case 1. These must intersect at a line. So we have intersection at a line. Now we're back to what I was talking about earlier. We have here two equations, 3 unknowns. That means I have more variables than equations. So I have one parameter I can introduce. More clear, or actually we can just do it without one if you guys want. You still want to try to make it upper triangular, like you're still interested in making this upper triangular. So typically what we can do is I'll multiply across by 2 here. So you get 2x minus 2y. We're still going to introduce that parameter, by the way, that we were talking about, but I think this will be clear for you too. Is 3. And I'll go through some more. See, if I still want to make this 0, right? I want to break this down so you still kind of get that upper triangular look to the matrix, right? Even though it's not a square matrix anymore, you still want to make it upper triangular. So by doing this here, subtracting these two, I create a new equation here. Notice if I subtract, so I took equation 1 and I multiplied across by 2, and we end up getting this. Now when I subtract these two, I've now canceled this off, and I'm creating here minus 2y minus 2y becomes minus 4y, and then 2z minus negative 2z is going to be plus what, 4z is 3. So I'll call this like 2 star. So now we have two equations. Equation 1, our first plane here, x minus y plus z is 3. And excuse me, and then equation 2 star minus 4y plus 4z is 3. Now I'm in a situation here like we were before where I have 3 variables, 2 equations. So like we were talking about, you're going to have to introduce a parameter. I'm going to let z equal t, where t is any real number. So the idea here is, like we were talking about, is z can be anything you want, because one of these variables has to be anything I want to be able to actually solve for the x and the y. So I'm notationally, they usually let the last letter of the alphabet be the parameter. There's nothing unique about t. You could have let it be r or s. I just picked t because that's typically values that are used for the parameter. So now that I know that z equals t, I can actually solve this equation, because this is known, it's the number 3, and this is now a known value. It's equal to t. You understand? So that means that minus 4y is going to equal 3 minus 4. It's not a z anymore, it's a t. And therefore y is going to equal negative 3/4 plus t. So the idea here is, like, you have this plane to solve for. You decide that there's a line of intersection. I try to start that process of making something 0, right? So I tried to knock it down to two variables, right? So I went ahead and doubled equation 1 and subtracted from 2. I created this 2 star equation. And then I took a look at my system, which looks like this. And I said, okay, I have 2 equations, 3 unknowns. I can introduce a parameter. So I picked the very last letter of the alphabet in the sequences that we had here, and I let it be parameter t. And now t is assumed to be known. So that means I can solve for y. So that means I have z and I have y. I can find x, right? By subbing this all in, I can find x. So therefore, x is going to equal 3 minus, it's not a z, it's a t, and it's not a y anymore. It's a minus 3/4 plus t. So therefore, x here is going to equal, you'll notice the t's cancel, and I get 3 minus 3/4, and x is going to equal what? 12 minus 3/4 is 9/4. Okay. So therefore, we have, my solution I'm getting is x equals 9/4, y equals minus 3/4 plus t, and z equals t. This is the solution of my line in parametric form, right? If I want to put this in vector form, the solution of my in vector form is going to be my point, which is 9/4 minus 3/4, 0, plus, this is your direction vector t. So this will be 0, 1, 1. Let me try another. I think it'll make more sense if we try another here. And I can do a bunch more. Okay, so let's try this one. So if I want to solve this one, the same analysis, right? The normal on the first one is 2 minus 1, 3. And the normal on the second one here is 1, 0, minus 3. So we can clearly see they're not scalar multiples of one another. Therefore, these two planes intersect at a line. Now, in this situation here, I don't have to row reduce anything. I don't have to reduce this equation anymore, because if I introduce a parameter, I can just solve for the other one. You see, like before, I couldn't really do that. Like it got a bit confusing, right? Like in the previous example, I had to kind of break this down to get a simplified equation, because if I would have just let the parameter be t right away, it still would have been a little bit messy to solve for. Here, I can just let, if you notice, I can let z be t here right away. I mean, you don't have to. Like if you want, you can multiply by 2 and make this 0, and you can solve it just the same. But I can just let z equal t, where t is any real number. And therefore, I know that x is going to equal 1 plus 3t. So like I've solved for z, I've now solved for x, and therefore I can solve for y. So therefore, what's y equal to? Well, y is going to equal 2x plus 3z plus 2. Right, but I know what all this is. This is going to be 2. Your x value is 1 plus 3t. Your z value is t plus 2. So therefore, y is going to equal 2 plus 6t plus 3t plus 2. So y is going to equal what? 4 plus 9t. This is parametric form, right? X, my solution I'm getting is x is 1 plus 3t, y is 4 plus 9t, and z is t, right? Where t is any real number. So this is the equation of the vector equation of a line in parametric form. If I want the vector equation of a line, which is kind of what you're more used to seeing, we've practiced that already. The vector equation of a line is you grab the point, which is 1, 4, 0, plus your direction vector t, right, is going to be 3, 9, 1. And that's the line that those two planes cross at.